Hello and welcome back to Differential Equations, section 1.4 on separation of variables for the sixth time in your life, I think. Right? Fifth? Maybe fifth. I don't know. But by now, you should all be the gods of, or at least demigods, of separation of variables because you have seen them so many times. Separation of variables is the method to solve first order differential equations where you separate variables of one kind to one side of the equation and variables of the other side to the other, and then you integrate both sides. So if you have some kind of a differential equation, let's say dy dx equals f of xy, let's say that's a standard way to write differential equation. Make g of y dy, or h of x dx, and then integrate both sides. And you have been doing this for a long time. If you have initial point, you will be able to calculate C, which would give you particular solution to go on. Now, since you all know the letters and numbers, you can read examples given in the book. I'm going to jump to the homework and steal an example from there. And the examples that are done in the book, just, read them. So, here's a cool one. It says dy dx, this is problem number 8. dy dx equals 2x secant y. They did not give us any initial condition. I can do another problem actually after this with the initial condition. We know the drill. Move the secant y to the left, move dx to the right. So this problem is like, oh, I'm going to have to integrate secant. Well, even if you did, you don't. But even if you did, right, integral of secant is ln secant plus tangent in absolute values. It's not the end of the world. But when you move the secant to the right and you leave 2x dx, move the secant to the left and then dx to the right, you see that 1 over secant is cosine. So you actually have a very simple problem to deal with. And you hit both sides with integral sign. You can kick the constant out like I did, or you can leave it in, whatever. Answer is going to be the same. So you have your sine y is equal to x squared plus c. And to come up with the general solution is going to be inverse sine of x squared plus c. And that's it. So all we have here is the general solution. And problem is solved. You can take the derivatives of this and blah, 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 try it here, make sure it all works out. One more example of these vanilla exercises, I would say. Here, problem let's go with problem 26. So dy over dx is equal to 2xy squared plus 3x squared y squared with y of 1 equal -1. So this is problem 26 in a textbook. And the way to solve this problem is to separate variables. And what I'm going to do is I'm going to factor out y's and shift them to the left. So dy dx is equal to y squared 2x plus 3x squared. And now we separate. So you get your dy over y squared is equal to 2x plus 3x squared dx. You need these parentheses because dx needs to multiply both of these terms. And now you hit these two sides with integral. Over here you have a negative 2 plus 1 would be negative 1. So this works out to be negative 1 over y is equal to, and on this side you have x squared plus x cubed plus c. You can solve for c here, or you can solve everything for y and then work out c. It doesn't matter. So if we are going to solve for y first, if I flip the fraction on the left, I flip the fraction on the right and then make negative. So y is equal to negative 1 over x squared plus x cubed plus c. So all of this was over 1. Then I flip the left side, flip the right side. And this over here, I'm going to still box and write general solution. This is what we practiced last time, general versus particular. But we do now have y of 1 equals negative 1, which is a point, which means x is negative 1 and y is 1. So once we plug those in, we will calculate c. So y is equal to negative 1 over negative 1 squared is 1 minus 1. Oh, sorry, y was 1. So negative 1 squared is positive 1, and negative 1 cubed is negative 1, and then we have a plus c. So this works out to be, oops, that I need to equal there. 1 is equal to negative 1 over c. Negative 1 over c. And clearly c is negative 1. I guess tablet is starting overheating. I would have to go get the cooling pad. I forgot. I should have done that before I started this lecture. So we finally have, well, actually, if I do this, y equals, and it was negative 1 over x squared plus x cubed and then minus 1. And this would be your particular solution. And that will be the end of the problem. So I'm going to get the cooling pad. I'm just going to leave you with one of these problems to practice. I mean, I'll be back in 30 seconds, but let's put dy dx. See, I can't even write when it overheats like this. It just doesn't work at all. It won't even scroll. Dy dx equals y times e to the x. So how about if I just try to write y prime equals, oh, writing slow is the key, y times e to the x. And then y of 0 equals 2e. All right, try that problem. Okay. Wait, did I do something wrong in the previous one? Oh. All right, by the time you finish this, I'm going to flip and change all of this. That's a -1. Now this is going to be 1 plus 1 plus c. So the negative is gone. And it's going to be c plus 2. I think. X is 1. Y is -1. And then plug in -1 for y. Good. X becomes 1. Good. Good. That's 2. It worked out to be -1 anyway. Let's take a look at this problem. Oh, this y looks awful. See, as soon as I cool the tablet down, everything is perfect. So, separate the variables. We're going to have a dy over y equal to e to the x dx. We hit both sides quickly with the integral sign. We get ln absolute y is equal to e to the x plus c. Then x equals 0, y equals 2e. Plug in. So that's ln of 2e is e to the 0 plus c. And is it 2e on the thing? Yeah, 2e. Good. So now this breaks down, if you know your pre-calc, into ln 2 plus ln e equals 1 plus c. Ln e is 1, so these two would cancel when you subtract 1 on both sides. And you get c is ln 2. So the solution is ln absolute y is equal to e to the x plus ln 2. And all I need to do is to fix this a little bit. I need to e both sides to get y alone. And over here I get e to the x plus ln 2. Now, the plus over here can be broken into e to the x times e to the ln 2, which gives us 2e to e to the x. So if I did all of this correctly, you get 2e to e to the x. And this is a particular solution. There's no c in it, as you can see, right? We calculated everything. This is a formula that is 100% ready for your input-output situation. And this is the one that you supply to the market, because it's simplified till the end. Now, if you give me that, let's say x is equal to, let's say 0, then I can compute e to the x is 1, and then I have 2e, so y equals 2e would be the answer. So I have a perfectly functioning function. Now, you know problems from before. We worked out all of those problems where you have the separation of variable, and in most cases you have you got a solution that you were able to massage into this function situation at the end. But in some cases you are not able to go that far. You are not able to change the function into expression into function, because expression is not a function. You cannot separate dependent variable from independent variable. They stay on a pile, and that is called the implicit solution. So we can have implicit solutions. Implicit solutions. And implicit solutions do come up, and you have to deal with those. Let me see if I can conjure up an example over here. What would give us implicit? Give me... these are all well, let's try with this and see. X plus y times y prime equal to 0. So y dy dx is equal to negative x, and y dy is equal to negative x dx. Yes, okay, good. This gives you a circle. So if you solve this, you get y squared over 2 is equal to negative x squared over 2 plus c. Now I know this is going to trigger some of you, but you'll get used to it. Times 2. Actually, before I trigger you, let's go and put this x squared over 2 plus y squared over 2 equals to c. And then I multiply entire equation by 2. And then I write it x squared plus y squared equals to c without multiplying it by 2. And then you go, what? You were supposed to multiply that by 2. What kind of noob are you teaching differential equations over here? This is something that you will see almost every day when we multiply the entire equation by a constant and we don't multiply c. The reason for it is that c absorbs all of the constants. And what you have here is the equation for a circle. Radius root c. So if you had the 2c there, or 3c, or a c, it doesn't make any difference. Your differential equation is correct whether that c is c, or 2c, or 3c. Now, those of you who want to call me out on this, go ahead, plug your solution in here with c first, then redo it again for 2c and redo it for 100c, and you will see that all of those solutions will work as a solution of a differential equation. So we don't put 2c because the problem is as good as with a single c, right? Solution is as good. Now, I am not given the critical point, the initial point, so I'm not computing the exact value of the c, so I don't have to worry about multiplying everything by 2 and blah blah, because if I had the point, I'd probably plug it in here and calculate the c before I even have to do this step. So this is done just for general solutions, right? You would absorb this, the c would absorb this too. And as I said, you're going to probably see this another 113 times in this course. We're going to do the same thing. So you will give up on trying to make it fit the algebra you learned in the first grade, because I know I had the issue with that as well, and I tried to argue with the professor, wasted 30 minutes in the class, and obviously got nowhere, because once I did what professor told me, which is what I told you, tried to use this solution with c, 2c, and 100c in a same differential equation, I saw that can just drop this nonsense and move on to the next problem. All right, so now what's next on the menu? Well, we want to talk a little bit about the better model for the population, for instance, because the model that we have so far is bad, right? The one model that you guys learned before with the population P, we saw it's good on a short term, but the long shot is terrible, right? Because if you, in the limit, send that model, so I'll put old population model. So if you send this old population model to infinity, you get infinity. And we know that we can't have infinite population on planet that has a finite surface area and finite resources, right? So we need a better solution to the problem to explain population. And for that, we are going to say that we're going to introduce birth and death constants, rates, and we're going to go into details later. I believe it's, let me just see what section. 2.1 is just population models. So we'll go into details then. Today I'm more interested in the way this stuff computes and what do you get in the end. So our good old problem is easier when we get into 2.1, which contains the full calculation and goes even further than that. So the question for us is to solve the differential equation that looks like this. dx dt is equal to ax minus bx squared. Right, so this is something we want to solve using separation of variables. And we just want to know what the solution looks like, and then I'm going to, when I go to 2.1, replace this x with p and call it logistic equation and call it solution to logistic problem, and then boom, we have a much better population model. Then you can also modify that and add harvesting. So let's say you have salmon like a salmon farm, which means that there will be birth of salmon and death of salmon, and then there will also be harvesting of salmon. So you will have you will be able to modify that with the harvest as well, which takes a couple of units periodically out of that. You can also use the same for crops, and so agriculture has a lot of problems, but then you can immediately import all of that into physics and chemistry and everything else. So these problems can become more than what it is. So here's the better model, and as I said, today is the lecture on separation of variables. So let's separate the variables and see what we get. In this case here, I'm going to have dx divided by ax minus bx squared equal to just dt. And on the left-hand side, we know we need to integrate both of these. Right-hand side is a joke. We don't have to worry about that. But the left-hand side is going to use Calc 2, which is why Calc 2 is the heavy prerequisite for this course. And it's going to use one of the methods of integration that I told you during the first class, you must know for a couple of sections and chapters in this course. Is anyone willing in the chat to tell me the method to integrate real quick by the time I solve the difficult right side? Just type it. Is anyone awake? Or you're already asleep? No takers? Partial fraction decomposition. Simple, right? So one person is awake. Okay, good. We have one. Hello. Partial fraction decomposition, where you have your x factored out, right? And you have a minus bx in here. Now, we're going to do a little bit more of this witchcraft to come up with values that we can deal with. So the first thing is, from algebra, we're going to remember that a minus b is the same as negative b minus a. So that's a very useful thing, because I know that I need to write this backwards. So it's going to be a negative, which I'm going to put upstairs, and then have a bx minus a over here. And then also for partial fraction decomposition, we know that we like to have that x alone. So I'm actually going to factor out b, and when I factor out b, I'm going to, so if I have bx minus a, and I factor out b, I'm left with x minus a over b. So now I can just define a over b as some other letter. It doesn't matter what you pick, because we'll bring it back later. So I don't know, m. That doesn't matter what we pick. So now my problem looks like this: negative integral dx. Now, negative 1 over b, because 1 over b we're going to kick out, and you're left with x, and in parentheses over here is x minus m, and you still have your t plus c on the side. And now we're going to just do the partial fraction decomposition to integrate the left hand side. I'm going to do this in a box on the side here. I have integral of dx over x minus m, and I'm just going to copy 1 over b obviously here, and then put my answer in there, and then have t plus c. So integrating this, I know that my setup is a over x plus b over x minus m equals to 1 over x minus m. And when I cross multiply, I get ax minus am plus bx equal to 1. Standard partial fraction decomposition from Calc 2. And I have that a plus b is going to be equal to 0. And negative am is going to be equal to 1. So a, the variable a, is going to be negative 1 over m. And b, naturally, must be positive 1 over m, because they need to add to 0. So I have my solution here in the box, which I'm going to now replace with parentheses. I'm going to have the constant a, and then the derivative, the integral of x is ln x. So negative 1 over m ln x, and then plus 1 over m ln of x minus m. A little bit crammed over here. There we go, fixed, fit. All right, now I'm going to factor out negative 1 over m, which would give me 1 over bm outside. And inside the parentheses, I'm going to have ln of x minus ln of x minus m. And the reason why I have a minus there is because I kicked the minus outside. So this negative went outside and made everything positive. And then this positive here turned into a negative. So now, all I need to do is to solve this x equals everything else, and I have my solution. So remember that your m was a over b. That's what we defined it, so we don't have to drag this a over b and do the denominators and all that nonsense. So now I can bring back a over b and cancel b. So this is 1 over b times a over b, and then these b's cancel, so it just becomes 1 over a there. And inside here, the subtraction of two ln's gives you the division of the arguments. So this becomes ln of x over x minus m equals to t plus c. And from there, we can go on and deal with the rest. Multiply both sides by a, right? So you remember how a is a constant that is going to be absorbed by c? Yeah, right? So when I multiply by a everywhere, I'm still going to write the c. So here's your number 2, 112 times to go in the course. So we're going to have, I forgot the absolute values, holy nightmare. Ln of x over x minus m is going to be equal to a t plus c. Next step is to e both sides, obviously, to fish out the variables. And that's going to be x over x minus m equals to, now this, remember that e to the at plus c is e to the at times e to the c. And see, okay, so now I'm just going to write this as, I don't know, capital M or whatever. Capital M or capital constant K. No, capital M, whatever. Capital M e to the at. So this became capital M. Now, why is this M? It's because, or whatever value, whatever letter you pick. Why is this capital M? Because E is a constant, C is a constant, and even if this was e to the ac, if you wanted to use ac when you multiply the whole thing by a to kill it off, even if you wrote it as ac, that ac would still be a constant. So constant, it will still work out to be an overall m in the problem. So this is the reason why when we're multiplying by number, this constant c always absorbs if it's a number. If it's times x, you have to write x, right? So it will be cx. But if you're multiplying by 2 or you're multiplying by a parameter a, then it gets absorbed and you don't have to. Anyway, so now that we clear that, we have this problem here. that spell meat. So you have x over x minus m equals to meat. All right, great. I have to remember this to solve it every time this way. Oh man. All right, cool. So I guess this problem doesn't work well enough if you're a vegetarian, right? Ah. So now we still need to get a single x. We had eat and then meat. Yes. Okay, yeah. So next part is to multiply this to the right side and then distribute, factor, and then get x's together, and you're done. So now we have x equals x minus m times meat. There we go. And we are going to now distribute meat into both of these. So x equals x meat minus m meat. And now we are going to move this one to this side so we can factor x's. So x minus x meat is equal to negative m meat. And now when I factor out x, I get 1 minus meat equal negative m meat. There I say clearly we need to now divide to get x alone. And that's our job, right? Anytime you're solving any type of equation, your job is to get x alone. Whether it's elementary algebra, when you solve x plus 2 equals, x plus 3 equals to 7, you subtract 3 on both sides to get x alone. In this case, you do a little bit more than that to get x alone. So we have a negative. Now, instead of m, we said that m is a over b, right? Or b over a. What was it? It was a over b. So now it's going to be negative a over b meat divided by 1 minus meat. There we go. Now, we can simplify this more. Technically, you are done, but this would be a terrible thing to give to a computer science person to write a code, because this could be reduced to less operations, right? You just have a lot of these. Like you have to compute meat twice and stuff like that. So how about we first multiply to oh, by the way, there's no more c. So now when you multiply by numbers, they have to stay. Okay? So now I'm going to multiply top and bottom by negative b first, which would kill the fraction from the numerator and the negative. So now you just have a meat. And on the bottom, they swap places. Because remember, when you're multiplying by a negative number, remember the formula from algebra that I had somewhere here? When you are multiplying by a negative, it swaps places, right? That minus sign gets absorbed. So when I multiply by a negative, meat goes first, and then minus 1, but they actually all get b's because you are multiplying by b as well. And there is one more thing to do. Divide top and bottom by meat because they can't, the meat cannot be 0, right? Because you have exponential function. Exponential function has a horizontal asymptote at y equals 0, so its answer can never be 0. And because it can never be 0, we can divide by it to simplify it. And when you divide by meat, top and bottom, you will only have one meat in the equation. So when we divide here by meat, and you divide here by meat, I don't know, it still cracks me up. I just by accident ran into this. I don't have notes or anything like that. It's not scripted. It's just whatever. Look what I get. The top meat just canceled, so you just get A. And on the bottom, the meat cancels. You get B minus B times meat. But you will have a negative exponent because it will be B over meat. And if you bring meat upstairs, it will be B negative AT. So it's no longer meat, it's now me minus AT. There we go. This equation is called logistic equation. And it is going to be used, right? This X will become population, and you will have A to be carrying capacity times initial population. So there will be some parameters and things for you to work on. What was capital M? Was E to the C? Okay, fine. So your separation of variables, right, are used to solve a lot of these problems. The last problem that I would like you to actually try and work on your own little bit before you go is Newton's law of cooling. And I'm just going to real quick get the English statement for it, and then we're going to convert that into mathematical statement, and then you use separation of variables to come up with the equation. So Newton's law of cooling states what? The rate of change of temperature, so change of temperature of an object is proportional to the difference between its own temperature and the ambient temperature. So this is observed in nature, written as a sentence, and then it's our job to convert it to mathematical equation, which is differential equation in this case, and solve it to get a formula which we can use to compute these temperatures. So when you think about this, is this sane statement, right, to claim? Is this something that it's okay to say? Well, hopefully you understand that if you are trying to bake something, there is a big difference whether you put it in the oven that it's 250 degrees or in the oven that it's 400 degrees. See, if you want to bake a chicken, right, or turkey or if you are vegetarian. I don't know what you bake if you're vegetarian. I'm not. Maybe you don't bake, I don't know. So if you want to bake a chicken and the chicken temperature needs to be 165 at the end of baking, can you achieve that with the temperature at 200? Well, yeah, 200 is more than 165. So yes, you will eventually, should I say. But if you stick the same chicken, right, in the oven that it's heated to 400 degrees, then it's going to be done faster. Because if your chicken is going into the oven, and let's say chicken was room temperature at, let's say, 70 degrees, so the chicken needs to go extra 95 degrees, right, to get to 165. Now, the statement says over here that the change in temperature in the chicken is proportional to the difference between the own temperature, which is temperature of the chicken, which is 70, and the ambient temperature, which is the oven, which you can set to 250, 300, 350, you can put any of that. So this sentence makes sense. The same thing with your coffee. This is now you say you're using Newton's law of cooling to heat up a chicken, right? Well, it's also cooling and heating. It's the same concept. It's just which way the temperature goes. Is it going up or is it going down? But it's the same equation, and it's just a minus sign that determines whether you are heating or cooling. So having your coffee cool on your table and having the same coffee in the same cup at the same temperature cooling in the fridge is going to be a different story. Obviously, the one that you stick in the fridge is going to be cooled later, faster, sooner than the one that you have just dangling out. So we have the temperature, and that's going to be the capital T. Then we're going to have initial temperature, that's called on, which is T0. And then we're going to have ambient temperature. In our case, with the chicken, is the oven. And usually people put capital R, but you can have TA, you can put whatever you want, no one cares. T is going to be time. You can do minutes or hours. And eventually there will be K. And I'll just say oven constant. Oven constant if you are baking a chicken. It's going to be a type and a shape of the cup, if you have a cup with the tea or coffee. If you want, now this is going to be some thermodynamics inserted here. If you want your coffee to be hotter for longer, and tea to be hotter for longer, make sure you are using a really fat cup, right? The one that is closer to the sphere. So the temperature dispersion is less if the object is closest to a sphere, because it has the minimum surface area to be in contact with the air, so it cools slower. If you want something to cool off quicker, just on the regular temperature, get a skinny tall cup. Then it will be now obviously I'm not talking about those thermal cups and stuff like that. I'm just talking about paper cup that has or has no lid on it. I don't care. The shape of the cup determines. So this K would play the role in what type of a cup it is, like what material, is it styrofoam or a cardboard or whatever, and plastic or glass. And then also in K would be the shape of it, whether it's tall and skinny or short and fat, in which case the coffee inside will stay longer. You are all welcome to do this experiment at home. If you have the temperature probe that you would use to poke into chicken or turkey as you're baking, poke it into a coffee, do the temperature reading, and then wait 30 minutes and do another temperature reading. Then change the shape of the cup and see what happens in the same period with the same temperature. Obviously, brew the same coffee and put in 2 different cups at the same time, because you're not guaranteed to hit the same brewing temperature if you do it from scratch. So you need to make 1 batch of coffee and put into 2 different cups and then do the measurements at the same time, so you can see what I talked about at work. All right, so now change in temperature divided by dt, right? Because that's change in temperature in time, is proportional. That's going to be this k, eventually work out to be the oven constant. The difference between its own temperature minus temperature of this is the temperature T0. Initial temperature, it's not the own temperature. You will get T0 from the calculation later on, because that C will turn into T0. This is the temperature of the object at that moment, not the initial one. I mean, when you put chicken that is on the room temperature 70 degrees into the oven, instantly T0 would be 70, but it will instantly start rising because it's in a 400-degree environment. So it's not going to stay at T0. So it's, initially it's at T0 and then starts rising, but it's its own temperature. Cool. This is, by the way, the own temperature right there. I'm going to, since we ran out of time, and this is way simpler calculation that it's than what we did for population up there, I will invite you that to solve this for your homework. And we are going to start our Wednesday class by working this out to get the Newton's law of cooling. Now, those of you obviously interested in mathematics and learning this actually, so because you will need it later on in your thermodynamics class and so on, and you want to practice separation, do this problem. It's a simple integration with ln, obviously, and you will be able to check online, because you can find these equations everywhere, right? For Newton's law of cooling, like 5,000 websites, maybe 500,000 websites with that equation there. Obviously, check the validity and sanity of the website. If the website is talking about Newton's law of cooling and about flat Earth at the same time, you're at a bad spot, right? So don't, right? Go to a different website. Now, guys, I'm planning on running Zoom parallel to the YouTube stream, so you can participate and ask questions easier. The link for the Zoom will be posted in announcements. That's why I said keep checking the announcements. I need you to be, present and active in class, so that you are learning the concepts. These concepts are not easy, and it's going to become harder and harder as we go on. We are still shoveling, Calc 1 and Algebra, technically, nothing special, but it's gonna get more interesting. So let's. So what I'm planning on is running Zoom parallel to the stream, and you log into the Zoom and you will see the same screen and you will hear everyone, except it's instant. It's not a 10-second delay like YouTube. So when I ask a question, you guys can immediately, as soon as I ask, you can answer and you can participate. And if you see something you don't understand, you can ask a question. Link for the Zoom will be in announcements, and YouTube will still go on, so nothing changes here. If you don't feel like participating, asking questions, and be there for pre-stream and post-stream shenanigans, then you just watch it on YouTube. I mean, whatever. Those of you, obviously, who want more immersive learning experience, join the Zoom. You will have the same lecture, and you don't even have to go into YouTube stuff. So all of that will be posted in detail. You will have the link and a password in announcements. I do not want to make it public, obviously, here on the channel, that it's public video. And I'll see you all either during office hours, which are also posted there in announcements on Canvas, links and times, and we'll go from there. Bye.